Welcome back to The Deep Dive, the show engineered to take the most complex, cutting-edge research, the stuff that determines the future of AI, and distill it into the crucial, actionable knowledge you need without the jargon overload.
And today we are addressing what is arguably the biggest, most stubborn bottleneck in large language model applications right now.
I think I know where you're going with this.
It's that invisible wall, the one that limits how much context an LLM can actually use without just, grinding to a halt. We are focusing on Retrieval-Augmented Generation, or RAGI.
RAGI is absolutely foundational. I mean, if you've been impressed by an LLM that can access up-to-the-minute stock prices or internal company documents or dense academic papers, that's RAGI in action. It's the essential mechanism that liberates the LLM from being this static brain trained only on historical data and transforms it into a dynamically informed expert. It's knowledge on demand.
Precisely. RAGI is the key to any knowledge-intensive application, but it introduces this fundamental, really painful trade-off that everyone running production LLM systems runs into.
Okay, what's the trade-off?
You can have a high context length, or you can have low latency. You cannot easily have both.
So the richer the context input we feed the LLM, and we want it to be rich, right? We want pages and pages of external documents, the greater the system latency becomes.
Exactly.
And the single most frustrating aspect of that latency is what we call TTFT, or time to first token.
That's the pause. That moment you ask the question, and the model just sits there, churning internally before it even begins typing the first word.
That dead air.
That dead air. And that churning is incredibly expensive. It happens because the LLM is forced to load and process all those thousands, maybe tens of thousands, of context tokens before it can do anything else.
And it's not just the computational cost of that initial load, is it? Every single subsequent token the model generates has to look back at all that preceding context using the attention mechanism.
Correct. And that's where the core issue really lies. It's memory, specifically the demands placed on the key value cache.
Right.
The KV cache.
Right. Always the KV cache.
For the LLM to attend to a long context efficiently during that generation phase, it needs to store the keys and values computed for every single token in that context. So more context means a ballooning KV cache.
Which requires a ton of GPU memory.
A ton of GPU memory, which dramatically increases the cost, and ultimately, it just throttles the overall system throughput, how many requests your model can handle per second.
So it effectively creates a knowledge ceiling.
Yeah.
We can make our LLMs incredibly knowledgeable by feeding them massive documents, but then we can't afford to run them in real-time applications if we do.
Yes.
So we cut the context and we sacrifice knowledge for speed.
That is the trade-off, and that's why we need to introduce REFRAG. That's representation for RAG. This new framework, which comes from research at Meta Superintelligence Labs and the National University of Singapore, is designed specifically to just obliterate that trade-off.
And the claims are genuinely transformative. I mean, they're not just improving things, they are breaking the RAG speed limit. What are the headline results REFRAG delivers?
The numbers are pretty extraordinary. REFRAG delivers up to a staggering 30.85 times acceleration in time to first token.
30 times.
30 times. To put that in perspective, that's taking an operation that previously took 30 seconds and reducing it to barely 1 second. And critically, they demonstrated this while maintaining the accuracy of the full uncompressed context.
That's a huge shift in the economics of deploying a RAGI, and I see it's not just raw speed, it's also about scale.
Absolutely. The optimization is so profound that it enables a 16 times extension of the LLM's context size. They took models like LLM-A27B, which natively operate with a 4K context window, and stately extrapolated their performance using context up to 16,384 tokens.
So it effectively supercharges the model. It's pushing its working capacity far beyond its design limits.
That's a good way to put it.
So our mission today is to move past the hype and truly understand the scientific insight that made this massive 30-fold acceleration possible. It all boils down to viewing the RAG input not as a generic, continuous stream of text, but as something else.
As a uniquely structured input that holds inherent exploitable computational redundancy. The realization that the input structure itself is the loophole. Well, that's the genesis of REFRAG.
Okay, let's unpack this structural realization. Because for most listeners, I think a long prompt is just a long prompt. It's a 16,000 token input. But the core breakthrough in REFRAG exploits a fundamental difference between a generic long prompt, say, a novel, and a long RAG context. What is that crucial distinction they capitalized on?
The distinction lies entirely in how the input was generated. A novel is a continuous narrative. A RAG context, by its very nature, is a collection of concatenated, discrete passages that are retrieved from a database.
Right, so you run a query, the retrieval system finds the top 10 relevant chunks of text, and then you just stitch them together into one massive prompt block to send to the LLM.
Exactly. And crucially, these retrieved passages have often been deliberately pre-processed, maybe by complex re-ranking algorithms that prioritize diversity or deduplication,
Why would they do that?
specifically to ensure that passage A covers a different aspect of the query than passage B. They are meant to be informationally distinct units.
So the input sequence is physically continuous, just one long string of text, but semantically, it's highly fragmented. Why does that fragmentation matter so much to the LLM's attention mechanism?
Because it leads to this unique, observable behavior within the transformer model, which they term block diagonal attention sparsity.
Okay, that's a mouthful.
It is, but if you visualize the complex attention matrix that the LLM generates when processing this RA context, you see a really striking pattern. The attention values for tokens within the same passage, say passage A, looking at other tokens in passage A, are massive. They form these dense, visible blocks right along the diagonal.
From diagonal blocks.
Yes, but then the attention values for tokens between different passages, say a token in passage A, looking at tokens way over in passage C, are minimal, often near zero.
So they form the empty off-diagonal sections of the matrix.
Correct.
It sounds like the model internally and structurally kind of learns to distrust tokens that are too far away in the sequence, especially if they came from a different retrieval chunk. It assumes, if I'm looking at the part about the symptoms, I don't need to waste computation looking at the part about the house's feng shui.
You've hit the nail on the head. That's the key insight. And it was a huge aha moment for the researchers. The model realizes that these retrieved chunks are not a continuous narrative, so it minimizes cross-passage computation.
Which means?
This means the concatenated ROGA context generates vast amounts of redundant computation. The LLM is spending tremendous resources calculating connections it ultimately just ignores.
We have to talk about the Bruce Lee case study from the paper, because this visualization is what made the empirical evidence so undeniable. They used a specific query on a real-world scenario.
It's an excellent illustrative anecdote. They used the Amine27B chat model, and they prompted it with a query about how Bruce Lee died. The RAG system retrieved 5 distinct, very complex passages, P0 through P4, covering a wide range of information and often contradictory information.
So give us the breakdown of those 5 distinct chunks. What were the LLM's inputs here?
Okay, so P0 focused on the more contemporary 2022 study suggesting water intoxication or hyponatremia, but it also touched upon the original classification of death by misadventure due to an adverse drug reaction.
Okay, so medical theories.
Right. Then P1 reinforced that water intoxication theory while contrasting it with older, more sensationalized theories like assassination. P2 went into those high-drama murder theories, Betty Ting Pei, gangsters, ninjas, even Dim Mak, and all the media speculation that came with it.
So you've got competing theories right next to each other.
Exactly. Then P3 provided detailed clinical information, his headache symptoms, the gobagesic painkiller he took, the resulting cerebral edema, and sadly, the cannabis theory, along with the later inclusion of the tragic death of his son, Brandon Lee. And finally, P4 covered the non-scientific cultural theory about bad feng shui impacting his residents.
So we have 5 highly diverse, complex segments just mashed together. In a standard LLM, processing thousands of tokens of this mixed input would require calculating every possible attention score between every single token pair.
Precisely. That would be a massive, dense matrix calculation. But when they visualize the attention matrix across Llama's upper layers, and these are the layers responsible for the most abstract synthetic reasoning, like layers 26 through 31, the data was just stunningly clear.
What did they see?
You saw strong high-value attention concentrated strictly along those 5 diagonal blocks, P0 on P0, P1 on P1, and so on. The off-diagonal attention, the required computation between, say, P0 and P4, was negligible, almost non-existent.
That visualization is the smoking gun. It proves that the vast majority of computation over the raw RAG context is computationally wasteful because the model ignores it anyway. It's paying for a computational luxury it doesn't even use.
And that's why the computational case for compression became unavoidable. Why should we spend precious time, memory, and energy calculating attention between passages that the model already knows are semantically distant and structurally sparse? REFRAG is the framework that finally exploits that sparsity. This is a subtle but really crucial distinction from just general LLM optimization.
So we understand the why the block diagonal sparsity demands compression, but now we have to address the how. How does REFRAG physically achieve this compression? And here's where my skepticism comes in. If we're adding a whole new lightweight encoder like Roberta Large to pre-process the context, aren't we just shifting the expensive churning from the LLM to the pre-processing step? How can we be sure we're actually getting a 30x speedup and not just moving the latency costs somewhere else?
That's a critical, absolutely valid question. And the architecture of REFRAG is specifically designed to prevent that very shift. The core is a novel hybrid decoding framework. It pairs the existing large, decoder-only foundation model year Llama 27B with a lightweight encoder.
Like Roberta Large.
Exactly like Roberta Large, which, at 355 million parameters, is tiny compared to the decoder.
So it's a hyper-efficient preprocessor that must be incredibly fast.
It is, for three main reasons we'll get to, but let's walk through the steps first. One, the context tokens, let's call them number of joule, are chunked into fixed-size, smaller units, dollars, using the chosen chunk size dollar. So, for example, K6 mothers dollars or $8.32.
Okay.
Two, the lightweight encoder processes these chunks in parallel, and that's a keyword, parallel, not sequentially, to generate a single dense chunk embedding for each group of teller tokens.
So a little summary vector for each chunk.
A perfect analogy. Then step three, a simple projection layer, usually just a small multi-layer perceptron, aligns this chunk embedding size to the decoder's native token embedding space. And finally, step four. The decoder receives the original question tokens plus this highly compressed sequence of projected chunk embeddings.
So if I have, say, 16,000 raw context tokens, and I use a compression factor of K332.2, I now only have about 500 of these compressed chunk embeddings to feed the LLM plus my original query.
Exactly. And this is the heart of the speed gain. It delivers three immense advantages.
Okay, what's the first one?
First, as you just noted, it dramatically shortens the decoder's input lengths from sentinel tokens to volatile chunks. That's the most obvious one.
Right.
Second, and this addresses your skepticism directly, the lightweight encoder processes those dollar chunks very quickly and, again, in parallel. More importantly, these chunk embeddings are pre-computable and reusable from the initial retrieval process.
So they can be cached.
They can be cached. So when a user asks a follow-up question, the encoder doesn't need to reread and recompress the context. It just pulls the compressed embeddings from the cache. This eliminates that redundant computation during the critical TTFT phase.
Okay, so the one-time cost of compression gets amortized across multiple queries or subsequent turns in a conversation. That explains why it doesn't just shift the latency.
It does. But the third advantage is the computational magic that explains the quadratic speedup, the change in attention computation complexity. In standard transformer models, the attention calculation scales quadratically with the number of tokens. That's the primary bottleneck for long contexts.
And what happens with REFRAG?
With REFRAG's chunk-based approach, the length of the input sequence the decoder sees is no longer to SPI, it's to lars the number of chunks. Therefore, the attention computation now scales quadratically only with the number of chunks.
Okay, let's make that concrete for the listener. If the lars is $16,000 tokens long, talar is an astronomical number, 256 million. But if our compression factor is $32, then low is only 500 dollars, and low squared is just 250,000. That's a dramatically smaller number.
Think of it like this. In the standard system, processing context is like searching a library shelf by reading every single page of every book one by one and calculating the relationships between every page. That's your 2 complexity.
Okay.
With REFRAG, we're only asking the LLM to read the index cards, the chunk embeddings for each book, and calculate the relationship between those index cards. That's the 2 complexity.
Yeah.
When that is thousands of tokens long, reducing that complexity from $2 to $2 is an enormous, almost exponential theoretical speedup, approaching 2K2 acceleration in both TTFT and throughput.
That transition from token-based complexity to chunk-based complexity is the mathematical engine behind that 30-fold acceleration.
Exactly. And there's one final technical capability that is just vital for modern applications. REFRAG supports compress anywhere.
What does that mean?
It means the system can handle mixed inputs, so compressed chunks and uncompressed tokens, at arbitrary positions in the input sequence. This flexibility is non-negotiable for agentic applications or multi-turn chats where you constantly need to interleave new tokens with compressed history.
We've established the architecture, but compressing context by a factor of 32, taking 32 tokens and boiling them down to a single embedding, that still sounds like a recipe for throwing away critical information. How do they train the system to ensure that the chunk embedding is truly a high-fidelity representation of the raw text?
That requires a highly sophisticated, multi-stage training recipe they call Crucial. It's based on continual pre-training, or CPT, and the goal is surgical alignment,
The surgical alignment.
making sure that when the decoder generates a response based on the compressed chunk context, it is virtually indistinguishable from a response generated using the full original context.
Okay, so what is step one in this delicate alignment process?
Step one is the reconstruction task, and it's a brilliant initial trick. The setup is straightforward. The system takes silly tokens, compresses them into louder chunk embeddings, and then the decoder is trained to reconstruct the original locus tokens perfectly from just those compressed embeddings.
That sounds simple, but I'm guessing there's a vital training constraint here that ensures quality.
The constraint is everything. During this initial reconstruction phase, the decoder model is frozen. The massive llama model remains completely untouched. Only the lightweight encoder and that small projection layer are actually trained.
Why freeze the llama decoder? Why not just let it learn alongside the encoder?
This is the analogy we need. Imagine training a student, that's the small encoder, to take a massive stack of 32 pages and condense it down perfectly onto a single index card. That's the chunk embedding. If you keep the professor, the large llama decoder, frozen, you force the student to make that index card absolutely perfect. The professor cannot just guess the missing information using its vast internal parametric memory. This explicitly encourages the entire system to rely solely on the context memory contained within that highly compressed chunk embedding.
I see. So if the decoder were unfrozen, it would likely use its existing knowledge to fill in the gaps created by poor compression, which would basically mask the encoder's failure.
Exactly.
By freezing it, they guarantee the quality of the compressed representation before they even move on to generating new tokens.
Exactly. So once that initial alignment is done, the decoder is unfrozen, and the system moves to next paragraph prediction tasks for CBT. But this introduces the exponential challenge, especially as they push for higher compression rates like K3 under 2 outers.
The challenge being that as the chunk length dollar increases, the number of possible token combinations the encoder has to learn to represent grows exponentially based on the vocabulary size. I think it's V dollars.
It is. It means the search space for reconstruction is just vast. It's essentially the vocabulary size raised to the power of the chunk size. The researchers observed that trying to jump straight into CPT on these long, compressed sequences, it just failed initially. They couldn't even reduce the perplexity.
So curriculum learning is essential to shepherd the system through that exponential complexity.
Yes. Curriculum learning incrementally increases the task difficulty, makes sure the model successfully masters simple compression before it even attempts to handle massive, context-spanning tasks. They start easy.
How easy?
For the reconstruction task, they begin by training the model to reconstruct only a single chunk, just $1 times K tokens from its single chunk embedding, Math BFC alone.
And then they gradually expand the scope from there.
They systematically increase the number of chunks to be reconstructed, moving from $1 times K tokens up to the full maximum sequence length, dollar chunks. This incremental difficulty is managed using a technique called geometric scheduling,
Geometric scheduling.
which varies the data mixture over 9 distinct training stages.
9 stages for data control is incredibly granular. How does that blending process actually work?
They literally blend the data. They don't just switch the data set midstream. So in the early stages, say stage 1 or 2, the data mixture is heavily skewed towards the easier, shorter reconstruction tasks, maybe 80% simple, single chunk reconstructions. This allows the model to stabilize and build confidence in its compression quality.
And then they shift the balance.
As training progresses geometrically, they shift the blend. By stage 5, they might be down to only 30% easy tasks, forcing the model to allocate the majority of its learning effort towards tackling the harder, longer, full-sequence prediction and reconstruction tasks.
That ensures robust performance. They observed that without this meticulously scheduled approach, the system simply failed to achieve high fidelity at aggressive compression rates. It is the backbone that guarantees the PMX speedup doesn't result in junk output.
We have established the architecture-fast, parallelized chunk embeddings and the training recipe that ensures the quality. Now we can move to the final piece of the puzzle, the sense and expand function.
Now, this part is brilliant. They realize that while this brute force compression is great for speed, it's risky if you accidentally compress and lose the one critical sentence. So how do they integrate a layer of finesse to decide, moment to moment, what tokens need to stay uncompressed?
This is handled by selective compression, and it's driven by a lightweight reinforcement learning policy. The system operates under a very simple hypothesis. Different context segments contribute unequally to the final generated answer.
Sure.
So we only need the full high-definition tokens for the segments that truly matter.
So the default is compressed, the index card. But if the system detects a crucial passage, it says, wait a minute, I need the full text here.
Exactly. The RL policies mechanism determines which small fraction of the chunks, let's call it tinny chunks out of the total dollar chunks, should remain uncompressed for the decoder input. The remaining majority stay compressed as those efficient chunk embeddings.
And what kind of fraction are we talking about?
They typically tested this using a high compression fraction where $0.111. That means 90% of the context is compressed and only 10% is expanded to full tokens.
And that 10% is the critical information the model needs to execute. The speed gain comes from ignoring the other 90% of sort of background noise.
The challenge then is selecting the optimal 10%. This selective compression is framed as a complex combinatorial optimization problem, choosing the best T-tiller chunks out of little total chunks to maximize a specific reward.
And that's hard to solve directly.
It is. Since this is a discrete problem, you either pick a chunk or you don't, and exact solutions are computationally intractable, they're NP-hard. They had to model it as a sequential decision-making process.
Which, as we know in the world of AI, immediately points to reinforcement learning.
Absolutely. They employ the powerful proximal policy optimization, or PPO, algorithm to train the policy network. PPO is the algorithm often used by foundation models, like the ones Meta uses for human alignment, when a system needs to make a discrete, high-stakes choice.
Like selecting the best chess move.
Or in this case, selecting the 10% of passages to keep uncompressed.
So the policy network takes the chunk embeddings as input and then sequentially selects the indices of the $2 chunks it deems critical. But what dictates a good selection? What is the reward function here?
This is the elegant part of the design. The policy network is trained using PPO to maximize a reward that is defined as the negative log perplexity on the generated output tokens.
Okay, let's translate negative log perplexity for everyone.
Right, so perplexity is essentially how surprised the model is by the next token it sees. Low perplexity means the model is confident and accurate in its prediction.
So it's a measure of certainty.
It's a measure of certainty. By maximizing the negative log perplexity, the policy is essentially getting a high reward only when its selection of uncompressed chunks leads to a very accurate, highly confident prediction of the next token. If it misses a critical chunk, its perplexity spikes and the reward plummets.
I see. This mechanism forces the policy to select only the context segments that are demonstrably most critical for generating an accurate, faithful, and coherent output. It's not just guessing, it's optimizing its selection based on predictive accuracy.
That combination, the brute force compression efficiency of chunk embeddings, coupled with the finesse of an RL policy that guarantees critical segments remain in high definition, is what makes REFRAG a complete solution. And because they continually pre-trained the system to handle these mixed inputs, this selective compression can be applied dynamically across turns in a conversation, maximizing efficiency every step of the way.
It's time to transition from the elegant theoretical architecture to the raw results. We've discussed the 30.85 times TTFT acceleration, but we need to put that in context. How does this stack up against the previous state-of-the-art compression methods, and what does it really mean for overall system performance?
The empirical results really solidify the breakthrough, and they focus primarily on Llama 2.7b for a clear comparison against existing long-context baselines like CEP and retrieval frameworks like REFRAG.
Let's focus on time to first token first, because that's the user-facing latency we all experience. That's the one that's most frustrating.
It is. So using their most aggressive setting, a compression rate of K3.2, REFRAG achieved a $32.99 times TTFT acceleration, compared to the original unoptimized Llama model.
Okay.
Critically, this translates to a 3.75 times speed improvement over the previous state-of-the-art memory-efficient long-context model, which was CEPE. And it did this all while achieving comparable perplexity scores. That gap 3.75 times faster than the best prior method is what signals a fundamental shift.
What if they used a less aggressive compression rate, say K1600 folders? Do the gains just disappear?
Not at all. With K1600 on 16,384 token context, REFRAG still achieved a 16.53 times TTFT acceleration when the chunk embeddings were cached.
Which they usually would be in a real application.
Exactly. Even in the worst-case scenario, where they had to recompute all the chunk embeddings from scratch, the uncached scenario, they still delivered an 8.59 times acceleration. In contrast, CEPE really struggled to maintain performance at those lengths, offering only about a 2 times acceleration in the cached scenario.
That uncached result is extremely important, I think. It validates that the lightweight encoder itself is incredibly fast and efficient. It confirms that Roberta Large, at 355 million parameters, is truly a minimized computational cost, and it minimizes latency even without relying on pre-caching.
Absolutely. The lightweight nature and the parallel processing capability of that encoder are non-negotiable for the system's success. It means the speed up is robust, even when you're dealing with entirely new context inputs.
And beyond that initial pause, what about the speed of generating subsequent tokens? Time to iterative token, or TTIT?
For iterative token generation, REFRAG achieved a reliable 3 times acceleration in long context scenarios. And when you look at the overall system efficiency, which is critical for cloud deployments, overall throughput, the number of tokens generated per second, was accelerated up to 6.78 times in the long context scenario.
And that throughput gain is what matters most for providers who are serving thousands of concurrent users, because it allows them to drastically reduce the required GPU resources.
Oh, absolutely.
The other headline benefit you mentioned was context extrapolation. Llama 2.7b is built on a 4K native window. We often need much more context than that in Ray.
And by transforming those context tokens into these highly efficient chunk embeddings, REFRAG was able to push stable performance far beyond that native 4K limit. They empirically tested and demonstrated effective extrapolation up to 16,384 tokens, which is 16 times the original window size when using the chunk-based representation.
Wow.
This fundamentally changes the applicability of smaller, faster models like Llama 2.7b to tasks involving, multi-chapter documents or large legal briefs.
The methodology seems robust. Was it truly model agnostic, or did they just cherry-pick Llama 2.7b because it worked well?
They conducted ablation studies specifically to address that, and they validated the training recipe on other decoder models, including Llama 3.18b and the even smaller Llama T's 3.23b. The result was consistent across the board. Models trained with the REFRAG recipe consistently achieved performance metrics comparable to the full context setting, even with high compression applied.
And what did they learn about the relative size of the components? Did a bigger encoder yield significantly better results?
That was an interesting finding, actually, regarding resource allocation. They compared using Roberta Base versus Roberta Large as the lightweight encoder. What they observed was that increasing the decoder size, moving from Llama 2.7b to Llama 2.13b, led to a substantial expected reduction in loss.
Makes sense. Bigger model, better performance.
Right. However, enlarging the encoder from base to large yielded only a modest improvement. The conclusion was practical. The benefit of a larger encoder is modest, especially if you have limited training data. This suggests that researchers should focus their resources on the LLM decoder and the compression training methodology rather than just scaling up the preprocessing encoder.
These massive speed metrics are great engineering achievements, but the true measure of success, really, is how these gains translate into better performance in real-world, knowledge-intensive RAG tasks.
Exactly.
It's a resource allocation problem, right? You have two choices. Use the speed up to run the same number of passages much faster, or use the saved computational capacity to run more passages at the same latency. How does REFRAG leverage this?
Let's focus on the equivalent latency comparison, as this is what really matters in a production environment where your response time is capped. They compared REFRAG using 8 compressed passages, what they call REFRAG 8, against a standard fine-tuned Llama model, Llama MAFT, using only 1 passage. The total system latency was equivalent in both scenarios.
So Llama FT is fast because it's restricted to just a single source, but REFRAG achieves the same speed while looking at 8 times the raw data thanks to that compression.
Precisely. So under a scenario with a strong retriever, where the passages are high quality and highly relevant, REFRAG achieved an average performance improvement of 1.22% across 16 standard RAG tasks.
That's a clear win. Same speed, 8 times the knowledge, and you get better results. The model just has more information to draw connections from.
Exactly.
But the real-world challenge is that retrievers aren't always strong. They can miss the mark, or they can include noisy or irrelevant data. What happens in the weak retriever scenario?
This is where REFRAG's advantage becomes much starker and, frankly, more economically valuable.
Yeah.
In the weak retriever scenario, the retrieved passages are less relevant or they contain more noise. The ability to quickly process a larger volume of context becomes absolutely critical because it increases the statistical probability of finding the one piece of useful information buried in all that noise.
Right. If LLM-FT is stuck only reading passage 1 and passage 1 happens to be noisy, it's sunk. But REFRAG can quickly skim 8 noisy passages.
And that leads to a significantly higher performance gain under equivalent latency constraints. So REFRAG 8 versus Llama FT1 REFRAG delivered an average gain of 1.93% in the weak retriever setting.
Almost 2%.
Almost 2%. The saved context computation is directly reinvested to include that additional information, enabling the model to extract more useful data precisely when the retrieval precision is lower. This is huge for real-world deployment where retrievers often operate under pressure and with imperfect indexing.
This essentially allows developers to make their retrieval systems a little less precise and still maintain a high answer quality, provided they use refrag compression. That's a cost-benefit win right there.
Absolutely. The system can afford to look at lower relevance passages that an older, latency-constrained system just couldn't afford to include in the context window.
Moving beyond simple question answering, how does this flexibility handle more complex, stateful applications like multi-turn conversations or agentic workflows?
REFRAG excels in multi-turn RAG and agentic systems because these applications constantly struggle with context history. The conversation history just grows longer with every single turn, constantly pushing the limits of the context window and demanding more and more resources for that KV cache.
And if you hit the context limit, you have to summarize or drop history, which leads to conversational drift and the model forgetting what you were talking about.
Right. So by efficiently compressing the past conversational turns into those reusable chunk embeddings, REFRAG models consistently demonstrated superior performance across higher numbers of conversational turns. They tested empirically at 2, 4, and 6 turns, and compared to the Llama fine-tuned baseline, REFRAG was consistently better. This confirms its robustness in maintaining state and leveraging context over complex dialogue tasks like Orcon VQA and Topio CQA.
Finally, let's look at long document summarization. This requires synthesizing information across an entire article, demanding a full view of a very long context.
This task is the perfect test case for REFRAG. They fine-tuned the model on generating abstracts for long scientific articles from ArXiv and PubMed. They found that REFRAG achieved the best performance when compared to baselines, under the constraint of using the same number of decoder tokens, meaning the same total processing time.
And what was the finding about compression rate versus quality?
Here's the counterintuitive result. A higher compression rate, specifically REFRAG 16, which compresses 16 tokens into one chunk embedding, performed better than a lower compression rate, REFRAG 8, when both were constrained by the same decoder token count.
Wait, why does compressing the input more aggressively lead to better summarization quality? That feels backwards.
It does, but it's not less information, it's less redundant input. The higher compression rate of REFRAG 16 allowed the model to incorporate a wider span of context from the full document. It could essentially read the index cards for a much greater number of pages within the same time budget.
Ah, I see.
By rapidly processing compressed representations of those distant sections, the LLM could synthesize a more complete view of the source material, and that led to better quality generated abstracts that were closer to the ground truth. They showed compelling examples of abstracts generated for complex papers on cardiovascular health inequality or spinal stenosis, confirming the high quality achievable with this compressed but wider view.
This has been an incredibly insightful deep dive. I mean, REFRAG doesn't just tweak LLM performance, it successfully dismantles the most significant performance bottleneck in retrieval-augmented generation systems today.
Absolutely. By leveraging that inherent structure, that observable block diagonal sparsity in retrieved concatenated passages, REFRAG fundamentally transforms the RAG context input from a costly Allison sequence of tokens into a highly efficient all-tail sequence of reusable chunk embeddings.
And the complexity doesn't stop at that brute force compression. It integrates a sophisticated, reliable training pipeline. The reconstruction task with the frozen decoder, the careful geometric scheduling for curriculum learning, and then it adds that dynamic control layer.
The RL policy.
Right, the RL policy that uses negative log perplexity as a reward to guarantee that only the truly critical context segments are expanded into high definition.
The result is a practical, scalable, and validated solution for deploying LLMs in the most challenging, latency-sensitive, and knowledge-intensive applications. It confirms a crucial developmental thesis, that RH systems are special, and they require specialized architectural treatment. Generic LLM inference optimization alone simply won't yield these kinds of speed and scale benefits.
So, REFRAG succeeds by exploiting the underlying structure of retrieved data. If our array systems consistently produce this kind of sparse context that benefits so dramatically from being compressed into these chunk embeddings, this raises a fascinating and I think a provocative question about the next evolution of our data infrastructure itself.
It forces us to re-examine the role of the database, doesn't it? Right now, we rely on vector databases and retrieval engines to give us vectors, and then we use those vectors to pull the raw text chunks. Then we spend time and resources using REFRAG's lightweight encoder to compress those text chunks into chunk embeddings to feed the LLM.
But since REFRAG proves that the high-quality compressed representation is what the LLM truly needs for efficiency, shouldn't the next generation of databases evolve not just to store vectors and text, but to natively support and flag this highly efficient compressed representation?
That's the question. If the database itself becomes chunk-aware, if it knows the optimal chunk size is $2 and it can generate that high-quality chunk embedding once, shouldn't it just store that embedding alongside the vector and the raw text?
So the LLM could access the compressed representation immediately upon retrieval.
Exactly.
That is, if the database did the compression work up front, we could eliminate the encoder step entirely during inference. We could enable even faster, more streamlined retrieval-augmented generation systems from the ground up, moving the heavy lifting entirely to the indexing phase.
That's the next logical frontier in optimization we have to consider if we want to move past the 30x speedup and aim for the 100x speedup.
Food for thought indeed. Thank you for guiding us through this cutting-edge research.
Always a pleasure.